the schedule reminds us that we're going to be looking at the first of the programming sets of topics. We originally had that scheduled before the semester break, but it seemed to be better to place it down here anyway. So we'll do that along with the first of the lectures on interpersonal communication tonight. Those lectures are available for you to download. You can listen to me droning away for quite some time about the information that's within those. I really want to concentrate in tonight's class session in demonstrating the programs that I talk about in those lecture slides, those PowerPoint slides. We can do the talking any old time, of course, but actually looking at the programs and filing them and running them and making modifications to them, I think is the sort of thing that we really should be doing and placing much more emphasis on. So we'll do that tonight. Then we'll. Oh yes, that's right. The programming part of the assignment. We've got a specification for that, and I'll go through that in more detail afterwards. And then yes, the exam, the mid-semester exam. I was scrambling to try and get the last of those marked before this evening, but that's going to have to be early next week now, unfortunately. I'll put all the marks up on the grade book, or what they call it these days, grade centre, and then I'll send a message around to everyone so that you can see what score against your name there. Okay, so yes, these are the topics. The stuff that talks about version and functionality and the POSIX stuff, that's a bit dry and not really as important as understanding how the real programming practice works. So I think that's what we'll concentrate on. I'm going to log into a Solaris box and use that to do the demos. You've got access to this too. I'll talk a little bit more about this when we have a look at the assignment specification in a little while. But the name of the server is called Rerun, and it's in the IT domain. And I log in as me, of course. You log in as you. And as it says here, it's a SunOS Solaris environment.
PS1. It's PS1.
Which is just fine.
We're the funniest people here.
That suits us. Yeah, that's a bit clearer. When we log in, who's never used a Unix box at all before? Rightio, no worries. When we log in character mode like this, terminal mode to a remote host, we'll, as soon as we log in, we'll find ourselves in our home directory. And I mentioned the home directory when I was talking about programming concepts. If I type PWD, that's just the working directory, and that shows the current directory that current working directory that my process has got direct access to, with of course the / being the home directory. If I type / run as being the root directory, if I type ls, that's the equivalent to the old DOS or Windows dir command. So that'll list the files in the current directory, and we get a better view of the characteristics of those though if we give ls the command line arguments -las, and when I request that, we can see that we've got a good deal more information that's useful to us, including not just file names now, but the attributes of the files that include me as the owner. So, of course, whenever I create a file, I'll be the owner of it. And when my user account was created on this machine, I was allocated to a user group. You'll be obviously in a different group. That's my group there. And you'll recall when we were talking about file systems in the material from the textbook, pre-mid-semester break, we talked about access control files. And I mentioned how in Unix environments, there are these three triplets here that we've got to control access to the files. The first three indicate what permissions I've got over the file that I've created. So I'm the owner of this particular file, make example, and I can do reading and writing and executing operations on it. Other people who are in the same group as I am, other users who are in the staff group, can do reading and executing operations on that file, and all other users in the system can do reading and executing operations on that file. The leading character over here tells us that this file is actually a directory. How do we define what a directory is again? Just in one sentence.
Organization unit for files?
Yeah, it's just a file that contains the attributes of other files as its contents. Okay, so those are directories there, and what else is interesting? Quite a few of the files here are ordinarily hidden from view. When I type ls up the top here, these are the files that were displayed, and of course most of those are directories. There's only one that's not a directory. There's a couple that aren't directories. Most of those are directories. And all these files down along here with the dot as the first character in the name, they weren't visible at all. They only became visible when I asked for the detailed directory listing. And that's okay. Those files are nothing special. They're essentially configuration or directories for configuration files, which most of the time I never have to worry about and never have to deal with. And so that's why the first character is a dot, to make them invisible, even though they're there, because most of the time I just don't have to worry about it. Okay. All right, that's fine. If I want to change the current working directory, I use the cd command, change directory, and one of the directories that I'll be fiddling around with shortly is the POSIX directory that I've just created. And in there, we've got some sample programs that I'm going to play around with shortly. Let's instead go to the root directory, so cd/, and have a look at the files that we've got down there. These vary, of course, from one flavour of Unix to another, but they pretty much reflect one of the diagrams that is in the PowerPoint slides that show you what sort of file structure you can expect to find in a Unix box. Right down here in the root directory, we normally haven't got read-write access, of course. I can't create a file and place there, not without super user privileges. But that's all right, we can still make it the current working directory. And if I go to the bin directory, you can see here there's a whole bunch of binary programs doing all sorts of stuff. Most of the time we don't really have to concern ourselves with where they are. They'll be available to us on the path, but the bin directory, as I've mentioned in the lectures, is where the binary programs normally live. There's also the user include directory, so that's where all the header files are for the Z programs that we might be creating. What else is, oh yes, the library directory. And I talked about static libraries and dynamically loadable, linkable libraries in the lecture too. This is all of those there. Lots and lots of them. I can't see any static libraries at all. And so the systems administrators of this particular machines look like they've decided to use only dynamically linkable libraries, which is fine. No problem. We can live with that. Oh yeah. The dev directory. This one looks like it's got files in it. However, they're not files. They are device special files. In other words, they are the device drivers or access to the device drivers in the operating system. When we want to get access to a device like a terminal device, then we open this device by referring to this object here by a file name, and that essentially gets us access to the terminal device. So even though these things here look like files, they're not. It's the standard Unix way of making files and devices appear to have the same interface. And we talked about that before. We mentioned that one of the advantages of doing that is that we can recycle the programmer's knowledge in accessing devices once they know how to access a file. And if we've all done embedded systems, I'm sure we have, then we know how to open a file for reading and or writing, and I'll show you that again here anyway later. And so getting access to devices is not very complicated now because of the way in which the devices are set up to look like files. Notice that the leading character in some of the device special files is neither a D for a directory or blank, as we would have seen with an ordinary file. This indicates that the device that we're dealing with is a character mode device. So this device here is a character mode device. What was the other type of device mode that we talked about when we had a look at chapter 13? There were character mode devices, and there were block mode devices. Give us an example of a block mode device. Yes. Give us an example of a character mode device. Sorry? Modem? Yes. Okay. These leading characters here, the lowercase l, indicate that what we've got is a symbolic link, which is actually the same thing as a Windows shortcut. So over here on the Windows desktop, we know that this little arrow down the bottom left-hand corner of the icon there indicates that this is a shortcut to the file, which resides elsewhere. Unix has had that around for decades. They call them symbolic links. And so here we can see that we've got a shortcut, if you like, in the current directory, which is actually pointing to the real file, which is elsewhere. Okay. Up yours, I think. If I just type CD and hit return, it'll take me back to my home directory. All right, so navigating around isn't too difficult. It's a bit easier to do when we've got a full graphical user interface to use on our Unix box, and that's a possibility too, as I'll show you shortly. But for the time being, this character mode will do us. We don't need anything more than that. What do I want to do next? Oh yes, that's right. What the other command that I mentioned in the PowerPoint slides was the env command, which is short for environment, and it tells us a whole bunch of essentially configuration parameters that our processes will inherit when they start up. And so any processes that I create now will inherit this environment. Right, so we've done ls, pwd, cd, env, the next one is ps. We want to list the currently running processes in the system. The ps command will do that. But again, like the ls command, it doesn't really provide us with a great deal of information. It's showing just the processes that I've got running at the moment, which is the command interpreter, born again shell. That's the program that I'm using here to type in the commands, command interpreter, of course, and the PS program, which I've run. That's the process ID numbers. There, of course, unique ID numbers are assigned by the operating system. But if we want to get a more detailed look at all the other processes that are running in the system, we can do that. And we'll see that it's actually a very busy server doing quite a lot of work. Many other users logged in, all doing their stuff, and we can see that it's obviously running a hypertext transfer protocol daemon. What's the more common name for that? Web server, correct? Yeah. And there are lots of other processes in there too, naturally, that we might be interested in if we decide to let ourselves get distracted by systems administration, but we won't do that in this subject. You might choose to do that in another subject. Okay.
Go nuts.
One of the earlier programs in the current set of PowerPoint slides that we're looking at allows us to identify what POSIX version we've got. And this is one that a tutor that used to work for me in this subject about 10 years ago, he wrote. And essentially it will include the header files that are important to us with respect to our level of POSIX compliance. What were those two header files that are the important ones? There are 4 header files up there, of course. See those. Oh, wait a minute. The next question is, who's never programmed in C before? That's a relief. All right, that's good. Okay, there are 4 header files at the top there. Which were the 2 that were particular to operating systems that offer POSIX compliance? We haven't looked at the lectures yet. It's these 2. So we include those 2 header files, and then we can find out whether the presence or absence of certain macros, certain symbols, with the presence or absence of certain macros, what's the level of POSIX compliant this particular operating system has. Who's never seen this sort of stuff before? All right. How does if-def, hash if-def, how does that differ to the ordinary old C programming statement if? How does if-def differ from if?
It's a preprocessor command?
It is a preprocessor command, that's right. Not the compiled instruction. What's a preprocessor command?
Something that's run on the text file before it's included, before it's compiled.
That's right. It's us telling the compiler to do certain things before it actually does the compilation operation. So we're saying to the compiler here, include these header files. So it does. It opens them and copies them into its current working space. And after it's done that, we're saying, all right, well, if this particular symbol is now defined, in other words, if this symbol here, _POSIX _version, if that is defined using the hash define preprocessor directive, obviously, in any one of those 4 header files, then we'll go ahead and compile these statements here. All right, so hash if-def is an instruction to the compiler, not an instruction for the compiler to compile and make object code from. Well, if this symbol is known, or if the compiler can see this symbol after including those 4 header files, then we've got a POSIX compliant operating system. Otherwise, all bets are off. And after that, we've got finer grain control over determining whether or not the operating system is POSIX 1 compliant, or whether it's POSIX 4 compliant. And if it is, what parts of the optional POSIX standard the operating system supports. And so this program looks a bit bizarre as far as many other C programs that you would have looked at is concerned, but because it's a program which is basically getting the compiler to interrogate the development environment for us. We're not really so much interested in having the compiler create an executable program. It does do that. But it's the real objective here is getting the compiler to open the header files and find out what sort of facilities and features, POSIX compliant ones, what sort of system calls are implemented in this particular operating system. All right, so let's compile that. I've already compiled it, but let's compile it again. So I want to do this a few times and show you how it compiles. That's what we're after. In the simplest way, to compile a C program in a Unix environment. We've got the GNU C compiler installed here. Even though this is a Sun machine, and they've got their own C compiler, most of the time the sysadmins install the GNU C compiler anyway, because it works pretty well, and it's free of charge, and everyone likes it. So the GNU C compiler is installed here, even though it's not the Sun native compiler. I'm telling it to compile with all warnings. So any code that I've created that the compiler thinks might be a bit sus, maybe open to misinterpretation, perhaps ambiguous, anything that it thinks should be drawn to my attention, I want to know about, because most of the time a warning means an error at runtime. Most of the time. All right, so I recommend you always do that too. I'm telling the compiler to produce an output executable, and that's going to be its name, POSIX check. And that means the compiler is going to do the compiling, and of course, it means the compiler is going to ask the linker to do the linking as well in an invisible step. And lastly, the particular C source code, C source file that I want to compile. If I've got more than one file to compile, I'll have to do each of those separately, compilation, and then do a separate linking step, which is a bit of a nuisance. We've got a special tool to help us get around that too, which I'll demonstrate shortly. All right, so we compile it, and then we run it, and we run it with just about all of these modern Unix environments. We run an executable program by specifying the path to it, because usually the current working directory isn't on the path. That's a security step. That's one small and reasonably straightforward way of avoiding Trojan horses. If someone else has installed an executable program called POSIX check, which is a Trojan horse, on this system, and I just type POSIX check and it runs that one instead of the program that I think I'm running in my current working directory, then I'm going to get things happening which I don't really want. And that can happen if someone manipulates the search path. And so I'll explicitly indicate to the command interpreter that I want to run a program called POSIX check in the current working directory. And that's what the dot and the / do. So dot / POSIX check. And so we do that, then the compiler has included the header files, processed all the preprocessor directives, and it's telling us that we've got a POSIX compliant operating system. That's good. The version is June 1995, and that it's POSIX 1 compliant and POSIX 4 compliant, and we've got these portions of the optional POSIX 4 specification available to us, which is good because we can do a lot of stuff with these. Real-time signals, priority scheduling, we've got timers, we can do asynchronous I/O, don't worry about file synchronization of map files, we can do memory locking, and we can do message passing, we'll see what that is tonight. Semaphores, we know about, we haven't seen them in action yet, but we're going to next week, in shared memory. And there are a few other administrative level features too that we're not so interested in. All right, that takes care of that. Let's have a look at a race condition occurring. Yes. All right. Here's, we know what a race condition is. That was one of the primary focuses of our attention in the first half of the semester. We're going to see a race condition appearing here. How do we define what a race condition was again?
Two processes try to access the same resources.
Yep. That certainly brings about a race condition. But in general, a race condition is a situation whereby the output from two or more processes is dependent upon the order in which they run. And we normally can't predict beforehand the order in which they'll run when we just let it go at the same time. Okay, so we don't like race conditions, but we're going to see one here just to satisfy ourselves that they do exist. They're not an abstraction that I just made up for the sake of it. So this reasonably simple program is going to use the fork system call to create another process. So we'll have an initial process on its own. It will make a call to fork. It'll generate another process. That new one will be called the child, and the original one will be called the parent. And the child process is going to print this character string here, world, with a new line escape sequence, and the parent process is going to print hello. And of course, the first program that we ever programmed, we learned how to program in C, was the simple hello world program that printed out those two words as one string. We've only modified that a little bit here, arranging for the parent to print out hello and the child to print out world. But we know that after the original process, what becomes the parent, has generated a new process, that the new one and the original one will run asynchronously to one another. All right. Again, I'll compile that, even though it's already compiled. But the more often you see this command, the better. Okay, now I'll run hello world and hello world, and it's generated two processes and it's printed them out, and what we get is hello world. And you're thinking to yourself, well, big deal. He's simply printed out. He's simply got a program that prints out hello world in two processes. We could have done it in one, and it all looks fine. There doesn't seem to be anything wrong with it at all. I'll continue to run it, and I'll continue to get hello world printed out every time. It looks like this whole race condition thing is a bit of a furphy. But what I will do is I'll write a small script, a shell script, that you can see at the bottom of the screen there, that's going to run hello world 100 times in succession, one after another. That just saves me typing it out all the time, or using the up arrow key to recall the previous command. So this is not the C program. This is a shell script, shell program, and it's going to run hello world 100 times, and we'll see whether or not that results in anything out of the ordinary. And in fact, it doesn't. There we are, finally. So after 300 runs, we discovered that on one occasion, the two processes were run in the opposite order that we would expect them to run in. Why did it happen there? We don't know. Variations in load that the operating system is dealing with. We know that it's running hundreds of other processes. It can't always guarantee to run the parent first. The parent prints out hello, the child prints out world. It can't always guarantee to do that. There's nothing in the construction of our program here that forces the operating system to always run the processes in that order. So it'll run them in whatever order it likes. And of course, most of the time, it would seem that it'll run them in the order that prints out the string that we expect to see. But there's no guarantee of that, of course. So every now and again, it's going to print out world hello, and that's not the output that we want, obviously. So in this case, our race condition is only exposed rarely. It's a statistically rare occurrence, this particular one, but that doesn't excuse it at all. The fact that it only occurs once in 300 invocations doesn't mean that our program is acceptable. It's certainly not acceptable. Okay, so there we are, race conditions, they really do happen. There's another one here which simply prints out hello world one character at a time, and that quite obviously produces a race condition. There we are. That one's a bit contrived. We won't bother persisting with that any longer, I don't think. Who wants me to go over again how the fork system call works? Excellent. All right. Who wants me to have a look at the fork system call again, or has everyone got that straight in their minds? We all know how the fork system call works. All right. Good. You picked it up quicker than I did. All right. Well, let's move right along then, and we'll have a look at signals, pipes, and message passing. Signals are where we started off. So there's a set of PowerPoint slides on Unix and POSIX signals, and what we've learned from listening to that is that signals are analogous to a hardware interrupt. They quite often get called software interrupts because they are events that occur asynchronously to their currently running process. And when they do occur, we jump off and execute a signal handler, and then we come back and resume the program from where we left off, just in the same way that we would execute an interrupt service routine when a real hardware interrupt occurs. Well, we'll do this example. In fact, what I'll do is I'll just modify it first. I've included the necessary header files, of course. The comment at the top there says it's a simple program. It installs a replacement signal handler for seek_int. We learned from listening to the lectures that the operating system installs default handlers for all signals. And when they arrive at our process, the default handler will be automatically invoked for our process if we haven't overwritten the default handler with a handler that we've created ourselves. And so what I've done on this occasion is I've arranged this program to have the process override the default signal handler for the seek_int signal, not for any of the other signals, just seek_int. And seek_int we can generate using Control-C from the keyboard, standard input device. As it says here, this is not a particularly good example because it doesn't reinstall the default handler before executing. And I've mentioned that in the lectures, but I wanted to keep this example nice and simple, so I didn't do that this time around. All right, this particular function here looks like any other ordinary C function, and it is really, there's nothing special about it. It will simply print out a character string, and we can call it obviously by name, just as we would do for any other C function. But this function here is going to be registered by the operating system as the handler for the seek_int signal now. So I need a seek action structure. I mentioned that in the lectures. I've placed in the seek action handler the pointer to the function. So ouch is a pointer to a function. Remember that in the C programming language, a pointer to an array has the same value as the name of the array. Remember that? A lot of people get confused about that, mixing up pointers and arrays. So a pointer to the first element of the array will have the same address value as the name of the array. Same deal goes for functions. So the address of the first instruction in a function, a pointer that is to the first instruction in a function, will have the same value as the function's name. So I've got the function name out here and placed that into the SIG action structure, which I've called act, in the SA_handler member. And so we've got a pointer to a function there now. The operating system requires that because when I ask it to install a new handler, I've got to give it the address of the function that I wanted to execute when the signal comes along. I've emptied the set by making it call the SIG empty set, obviously, and giving it the address of the SIG action structure. And I've tested to ensure that the call to SIG empty set was successful by having a look at the return value. How do I know what the return value should be? I've just put if SIG empty set with the argument returns value that's less than 0, then we've got an error. But how do I know what a good return value is from a bad return value? Well, I can look it up, and that's precisely what we should be doing. And I'll do that now. Man SIG empty set. There we are. So I've used the Unix manual page here to find out about the SIG empty set system call. And I can find out by having a good close look at this what the return values are. There we are, return values. Upon successful completion, the SIGIS member and the others will return a 1 or 0 if it's not. On successful completion, the other functions return a 0. Otherwise, a -1 is returned. An error number is set to indicate the error type. So for the system call that we're after, we can find out all we need to know about it, in fact, in much more detail than we would normally need, by using the Unix manual pages. So we've got a built-in online reference there that we can make use of at any time. I showed you in the lectures how to use the Unix manual, or there's a demonstration of how to use the Unix manual pages for one particular system call. Say for example, I've forgotten how to use the Unix printf function, and I need a reminder on how to use that. If I type command printf, sure enough, I've got printf here, but having a good close look at it, it doesn't actually look like the standard C runtime library printf function. I can't see printf looking like the printf function that I expect to see. Like here's an example. That doesn't look like the C printf function. That certainly doesn't, because we know what we know enough about printf to remember that after the keyword printf, the first symbol that we should find, other than white space, is an open bracket. So what's the problem here?
Wrong man page.
Yeah, that's right, mate. Wrong man page. This is printf, all right, but it's not the C runtime library printf. It's printf for the shell programming language. So what I would have to do is instead remember that the Unix manual pages are split up into sections. Section 1 is user commands. Section 2 is system calls. Section 3 is libraries. And the one I'm after is the printf in section 3. But the Unix manual tool has started searching through section 1, and as soon as it's found something that matches my request, it's given me that. It's given me stuff in section 1, the user command stuff. I don't want that. I want the stuff in section 3. So I would do this instead. no printf in section 3 of the manual. All right, well, how do we find out where printf really does exist? We'll use the -k option, as I've pointed out in the lectures, and get the Unix manual to search through all of the sections that it has and find references to printf. And we can see that, oh yes, it is section 3 that we're after, but it's section 3C for the C programming language. So that's how it's structured here under this SunOS Solaris. So again, to find out what I need about the right. So I specify section 3C of the manual, and sure enough, it finally gives me the specification on the printf function as it pertains to the standard C runtime library, the formatted printing statement. And I can find out all I need to know about printf that I might have forgotten. Okay, so back to the signal example. We find out what return value that we would expect to get from SIG-empty-set by using the Unix manual page. If we've got a web browser handy, and we usually will have, we could point our web browser at the POSIX standards page anyway, and get that same information and render it in our web browser instead of from the online manual pages. The advantage in using the manual pages is that they're installed locally and are definitely the correct versions for the development environment that we're actually currently working on. If you use a web browser to look at some other website to tell you how all these functions work, there's a good possibility that they're talking about slightly different versions that run on slightly different environments, not the ones that you're actually using. So your mileage might vary. Okay, I've used the SIG action system call here to tell the operating system that I want to override the default handler for the SIG int signal, and I've told it to look in the SIG action structure, so the address of the action structure, look in there for the information that it needs, which is essentially just the pointer to the handler function. And again, I've checked to see whether or not the return value is less than 0. And if it is, I'm going to print out an error message so that I know why my program isn't executing properly, and then I make a call to exit. Same sort of thing I've done up here. So I print a message to the user, SIG-empty-set failed and terminating, and then we do terminate. Or here, SIG action failed, so a different system call, terminating, and again, terminating. What do these little numbers in here mean? Exit 1 and exit 2.
The error code.
Yeah, they're error codes that I can use if I'm running this program from another program. If I'm running this program from the command line, I'll probably find all the information I need just from the strings that are being printed out to tell me why things aren't working. But if I'm running this program from another program, if I'm getting some other program to run this, it would be easier for that other program to be informed of the type of error that we've discovered by giving it a number instead of a string. All right. As it says down here, if we've got this far, then our two system calls have been successful, and so what we're going to do is we're going to go into a continuous loop construct where we print out a string and then sleep for a second, and then print out the string again and then sleep for a second, and continue to do that until the signal arrives. So we've got our process doing a little bit of busy waiting here, just until the signal arrives, and that's okay because normally we would avoid busy waiting, but we're intentionally doing it this time because we're attempting to test out how our signal handler is going to work. Right. What I'll do is I'll actually, as I mentioned before, I'll modify the program so that it doesn't have the signal handler installed. So what I'll do is I'll just comment out the system call that I made to ask the operating system to install the handler. So that's all that's necessary to have the program set up so that the default Control-C handler will be in place. All right, so even though I've created this structure up here and I've placed information in the structure there and emptied the set, I haven't registered that that structure and its handler with the operating system because I've just commented this bit out. In fact, what I'd better do, of course, is comment all these out. Otherwise it will execute those, and we don't want that. So here we've got a program which is pretty much normal in the sense that it doesn't have a Control-C handler installed, and when we run it, it will enter the continuous loop construct, doing what it's supposed to do, sleep for a second, print out the string, sleep for a second and print out the string, and asynchronously to that running process, of course, I will send it the seek-in signal. So when I hit Control-C now, the standard default handler for the seek-in signal, the Control-C signal, takes over and it terminates the process. That's the standard default behaviour. That's what we would expect to see. But if I install the signal handler now instead, in other words, if I ask the operating system to use my seek action, my signal handler instead of the default one, recompile obviously, and run it. Now, when I supply the seek int signal, we should see my default handler be automatically invoked, my handler invoked instead of the default handler. And sure enough, it does. So we're supplying Control-C, but instead of the operating system's default signal handler catching that signal and terminating the process, the normal behaviour, I've got it executing my function instead. And that leaves me with a problem now, doesn't it? All right, well what I'll do is I'll send it another signal that it's not expecting. And of course the default handler will be invoked again. Bingo. All right, so what have we learnt there? We've seen, after listening to the lectures, we found out what these signals are all about. That they are excellent ways of avoiding busy waiting by having our processes being notified of asynchronous events, I/O events, exceptions, things like that occurring. And if we want, we can have the default signal handlers modified. We can create our own and have the operating system register those instead. That's handy. I also mentioned in the lectures that there's another very simple signal called the alarm signal, we'll have a quick look at this one too. This is probably the simplest example of all of the sample programs. It demonstrates the alarm system call. We give the alarm system call an integer variable, and that'll be, it must be an integer, and that'll be the number of seconds that the operating system will count down until it delivers the seek ALRM signal. And in this case, I haven't created a new function handler for the operating system to install. So we'll set up the alarm, it'll count down for 9 seconds, and then the default handler will occur for the CALRM signal. I won't bother compiling it again in front of you, it's all been compiled. Right, so when it counted down to 9 seconds, the CALRM signal was generated by the operating system kernel and sent to our process, and the default handler dealt with it. Have a look what we printed out. It says alarm clock. Whereas when we have a look at our program source code here, the string alarm clock doesn't appear at all. So where does that string come from? And the kernel's given us that. Yes, thank you, Kernel. All right, so signals, very good for asynchronous event notification. We can avoid busy waiting. We can have our process suspended until the signal arrives to wake it up to do something if we want, using the sync suspend system call, and I've described that in the lectures there. And as we've already seen, we can override the default signal handlers by installing our own. That's fine, and signals are appropriate when we've got asynchronous event notification, but they're not much chop if we've got messages that we want to pass, because the signal is a single 32-bit number, and there's not very much information we can store in a 32-bit number. When we want to experiment with message passing, we've got in the POSIX environments, we've got three different techniques we can use. The simplest one is the standard Unix pipe, which is what we've got here. And again, this is all described in the PowerPoint slides. And here, in this case, we've got a very simple pipe demo. The parent is going to write a string into a pipe, and the child's going to read it and then print out what it gets. So, very simple. Two processes, a pipe in between them. The parent writes into the pipe, the child reads from it, and then the child's going to print out what it reads from the pipe. There is the integer array that I mentioned in the lectures that is necessary to store the pipe reading and writing file descriptors. And there is the call to pipe. So we ask the operating system to create a pipe for us, and we give it this integer array here. And if the operating system is successful in creating a pipe for us, then it will plug some numbers into that array. And those numbers will be the reading file descriptor and the writing file descriptor for the pipe. Again, if the operating system doesn't create the pipe for us for whatever reason, then we need to know about that. And in this case, I've used the p-error system call instead of the printf, because p-error provides us with a little bit of extra information. I'll demonstrate that one more effectively in a moment when we have a look at the next example that talks about named pipes. So bear that p-error thing in mind. We'll get back to that shortly. As it says, the comment says here, we'll print out the file descriptor values. Ordinarily, we're not worried about their actual numeric value, the file descriptors, but this time around we'll print them out just to show that they're ordinary old integers, or look like ordinary old integers, and there's nothing special about them. However, from the lectures, we would have noted in two separate places that the first three integers, 0, 1 and 2, are set aside for as special file descriptors. Who can remember what special devices 0, 1 and 2 file descriptors are allocated to? The standard input device is always file descriptor 0, the standard output device is file descriptor 1, and the standard error device is file descriptor 2. All right, so we create our pipe and we check to make sure that the pipe has been successfully created for us. If not, we terminate our program after printing an error message. If it is successful, we'll print out the values of the file descriptors just for each sake. The next step is to create a child process. So same deal as before. Make a call to fork, capture the PID. If the operating system didn't create the child process for us, then we need to again print out another error message to terminate. Otherwise, we have got a child process, and we can execute the instruction. We can get the child process to execute these instructions down here, and have the parent process execute those ones there. And that's quite straightforward. We've got here in the parent process, we've got the string of characters that we're going to have the parent process put into the pipe. Because the parent process is going to be doing the writing operation, we can close the reading file descriptor, and we use the ordinary old file system write function, referring to the writing file descriptor with a pointer to the first character that we want to write into the pipe. So there is the uppercase T there. The uppercase T is referred to by that address for into the pipe, and then the number of characters that we put into the pipe. So this looks exactly like it would if we were writing these characters into a file to store on disk. However, we're doing message passing. We're not writing to a file. We're having the operating system copy all those bytes into the kernel space, and then copy them from there to the child process. Because the child process is going to be receiving the characters, we give it some storage space, and that storage space takes the form of an array of characters. And we close the writing file descriptor there. And then, again, just as we would do if we were reading characters from a real file, we'll read characters from a real pipe. I'll append a null character to the end of the string there, that one gets omitted, and then I'll use the standard printf with the string format specifier to print out the characters that we've got from the pipe. Alright, so if we compile that in the normal way, GCC space www blah blah blah, then we'll get a compiler to compile our program, and there we are after we've run it. So the call to pipe is successful, the file descriptors are 3 and 4. That probably makes sense, since we already know that file descriptors 0, 1 and 2 are spoken for. And these characters here have been through the pipe. Having a look at this program again though, it might seem a bit contrived. It might seem that since I've got these characters in this same program, which has been shared by the parent-child, that I could have cheated and just get the child to print those characters out without going through the pipe. But that's actually impossible. Can't possibly cheat. Why is that? It can't possibly print out those characters without them going through the pipe. Why? Even more fundamental than that, it's actually the C programming language which is forcing this to happen. Bit surprising, isn't it? Remember that the C programming language has block scope. What does that mean? Variables have block scope.
Means they don't exist outside their function?
That's right. In fact, it doesn't exist outside this block. Because that array, character array, called pour into pipe, because it's been created inside this block, it doesn't exist outside that block. The programming language is enforcing that. We haven't even got to the operating system yet. And there's no printf statement inside that block. The only place in the program code was the printf statement is down here. And of course, because this variable, it's an array, but it's a variable, because that variable is restricted in scope to that block, any reference to pour into pipe down here means what? Program won't compile. Because that variable, pour into pipe, isn't visible down here. Right, so the C programming language, with its scoping rules, is forcing us to output only what we get from the pipe. I can't take any shortcuts and just print out the array. So the only printf statement in this program is in this block here, the block that's executed by the child. There's no other. Oh, there's that printf statement up there, of course, but that's before we've even got a child process. And then, obviously, that printf statement there cannot print out pour into pipe. Pour into pipe hasn't even been created yet. Right, at the time we execute that instruction, pour into pipe doesn't exist. So there's no way in the world that we could possibly have cheated in this particular example. The only way that those characters can be printed out is by sending them through the pipe. So our program won't even compile. You can try that yourself later if you like. If you edit this code and put pour into pipe there instead of collecting pipe, pour into pipe, it won't compile. Fantastic. All right. What's the problem with good old-fashioned Unix pipes? What's the main problem? No. Now the main problem is that we can't have any two arbitrary processes get access to a pipe. The hassle is that this pipe here has to be created before the child process is created, so that the child process inherits the file descriptors. So there has to be a common ancestry between the two processes if they're going to be using a pipe to exchange information. So if we're going to use pipe message passing, we can only do it between processes that have a shared ancestry, either parent to child, or parent to grandchild, or whatever. And that's not very flexible. What we would prefer is the ability for any two arbitrary processes to be able to talk via a pipe. And that's what we get with named pipes. Named pipes are also called FIFOs. That's a bit unfortunate because the acronym FIFO gets bandied around a lot. It gets used to mean all sorts of things. It pops up all the time with different contexts attached to it. But in this instance, when we're talking about message passing, and we see FIFO, it means first in, first out, named pipe. How do named pipes work? Well, they work by creating a pipe, but giving it a name and file system. Just like we saw these device drivers down here having a name and file system, they look like files, but they're not. We can create a pipe that looks like a file, but it's not. All right, it's a message instead, or a message passing structure in memory. Okay, let's see how that works. We've got a couple of programs here which demonstrate that. I'm going to have a look at FIFO A demo first. Okay, this program creates FIFO in the /temp directory, and it waits for another program to put something in the FIFO, and then it prints out whatever it finds in there. All right, so this time round, we're not using the fork system call. We don't have to anymore. The FIFOs have got that extra flexibility. We can have any two arbitrary processes access the FIFO. So this process is going to create the FIFO and then wait for another process to put something in it, and then it's going to print out what it finds. All right, well, we've included a whole bunch of header files here. How do I know which header files to include? Do I include all my favourite ones and hope that's enough?
Yeah, and if the compiler throws you an error, just include another one.
Sorry, mate?
And if the compiler throws you an error, include another one.
Yeah, that's right, include more.
It'll optimise.
Well, the Unix manual page tells us. So where I've used the MK FIFO system call here to make the FIFO, that's what we're going to use this time around instead of a pipe. So we don't make a call to pipe, open brackets, integer name, integer array name, close brackets. We don't use pipe anymore. We use MK FIFO. Again, that's in the PowerPoint slides. If I want to find out about what header file I need, yet again, we've got FIFOs available from the shell. There we are. It's telling me I need to include both of those header files. Angle brackets sys /types and angle brackets sys /stat. So I need to include both of those before I can use MK FIFO. Well, that's handy. It takes a bit of the guesswork out of it. All right. So I've included the correct header files, and I've included my own user mode header file there between the double quotes, of course, saying that it's an absolute path rather than the system path for system header files. It's an absolute path, and it means it's in the current directory. We better have a quick look at that. There's not much to it. All I've done in there is put the name of the FIFO, because these are named pipes, so there's its name. And its name is my demo FIFO. It's going to be in the temp directory. And I'll put in there another macro that that both programs need, and it's just the length of the message. Okay. If we have a look in the temp directory, we can see there's a whole bunch of files in there that belong to other people. How do we find out who belongs to what? We use ls-las to get a more detailed listing, and we can see, yes, there's lots of other users have got temporary files in there. These are all the usernames, and these are the groups that the users are in, and these are the temporary files that those users are using, whether they're aware of them or not. Okay, so the //tmp directory is a world, an all-user accessible directory where we can put scratch files, temporary files. And that's where I'm going to put my named pipe. I called the named pipe. I called it my demo FIFO. So we'll just check to make sure that there's no named pipe called my demo FIFO already in the temp directory. So my demo FIFO. No, that's a trial directory. Okay, good. So there's no named pipe already in that directory, and we'll see what happens if there is in a moment. So getting back to the actual sample program. We make a call to MK FIFO. We specify the FIFO name. That's from the header file. /temp/my demo FIFO. And then I'm asking the operating system to let other processes that are owned by me, the same user, to get access to the FIFO. So not other users in the system, but just other processes that I'm running. And again, I check to make sure that the operating system has been able to create a FIFO for us. I don't just assume that it's been successful. And I've used the p-error system call, if something goes wrong, to indicate that it's the make FIFO system call which has failed. And then we'll terminate again. If we get past that, then it means good. Our FIFO has been successfully created, and I'm just printing a message out to the screen so that I can see that that's occurred. and we're waiting for some other process to come along and write into the named pipe now. When some other process does do that, what we'll do is we'll open the named pipe for reading. So up here we've created the named pipe. Here we're opening it, just as we would open a file. We open it for reading, read only. Again, referring to a pipe name. I double checked yet again just to make sure that that system call has been successful, because maybe I've created the FIFO and everything's fine, and then the super user comes along and cleans up the temp directory and destroys my FIFO. Maybe it disappears. So I can't presume that the open operation is going to be successful even immediately after the make FIFO operation has been successful. So we program defensively and always check our system calls. And you should do that too, always check system calls. So if we've been successful in making the FIFO and opening it, then all we need to do is to wait for some other process to put some information in it. And so we'll do the standard file system reading operation there. We'll read, referring to the descriptor, file descriptor, and the same as before, a pointer to a series of memory locations where we can store the message, and that's an array, and the number of characters that we're going to read. If it turns out that nobody put anything into the FIFO, then the read system call will return 0. Number of characters that are read, 0. Nobody put anything in the FIFO. It was created, it was empty, and stayed empty. Otherwise, someone did put something into the FIFO, and again, I will append a null character to the end of the string, because that gets stripped, and I can't use the printf function properly unless there's a null character at the end of the string. And so I'll put the null character at the end of the string, and then I'll print out what we got from the FIFO. Then we close the FIFO, because we opened it here, we close it there, and because we made the FIFO the file system up here, we should unlink it from the file system down here. That actually removes it from the test directory. Okay, that's the unlink operation. And yet again, we check to make sure that that system call was successful, and if not, we'll make a call to P error and refer to the unlinked system call as the one which was unsuccessful or failed. Right, so that's the more complicated of the two programs. The other program, this is the one that's going to take the FIFO that's already been created by the program we just looked at. So this is a completely separate program. It's going to take the FIFO, open it, and write into it, and then close it. That's all it does. So in its entirety, that's it. It doesn't have to make the FIFO, of course. The other one made the FIFO. So all it has to do is have its message, the message it wants to put into the FIFO, open it successfully, and of course open it for writing, WR only, write only, and then write into it, just using the file system write, then close it, and then exit. It doesn't have to do the unlinking operation either. It shouldn't do the unlinking operation because it didn't make the FIFO. It only opened it, used it, and closed it. So the program that made the FIFO should be the one with the responsibility for removing it. All right, I'm going to open a separate terminal and log in again, so that I can run one program from one of these terminals and the other one from the other. And that should give us a better demonstration. I'll just make this a little bit clearer for everyone to see. All right. So I've got two Honey terminal sessions connected to the same server, and I've got the same working directory in each. Over here, I'll run FIFO A demo. That's the program that creates the FIFO and waits for someone to write into it. It's going to wait there for as long as it takes. If we, in the other terminal session, looking in the temp directory now, we should see the FIFO itself. It should be there now. There it is. Created at 16 minutes past 7, which is about right. And I'm the owner, and that's the group I'm in. And of course, I've got reading and writing control over my pipe. That's the way in which I created it. Remember, I can read from it and write to it. And this leading P here indicates that it's actually a pipe, a named pipe. Again, it looks like a file because we've typed ls-las and we can see a listing of files, and there's a name in there, and it looks like a file like all the other files. But this is reminding us that it's not a file. It's actually a pipe. That little P there, which I can't select, that P is telling us that it's a named pipe. It appears to be a file, but it's not. It's just giving us access to it through the file system. All right. So the file is there. The pipe is there, and what we can do now is run the other program. So this is the one that opens it, writes into it, and then closes it again. And as soon as I hit return, it'll run. And if all goes well, we should see in the larger terminal window, the first program will discover that there's something being put in the pipe for it, and it'll print out the message and it'll terminate. Okay, good. If we run this one again and create the pipe for a second time, and then if something goes wrong, I send this process the interactive termination signal, Control C. So before the other process has had a chance to open the named pipe and write into it, I've terminated the original process. Then what do you think's happened to our named pipe? Yeah, it's still there. So we've terminated that process before it got a chance to get rid of the pipe and get left around. If I try and run this for a second time, we're going to strike a problem because it's going to try and create a pipe with a certain name in a certain location and discover that there's already one there. Yeah. So if we have a look at the source code for FIFO A demo again, down here where we ask the operating system to make a FIFO for us, if it strikes a problem of some sort with that command request, that system call, then we make a call to P error and we refer to MK FIFO as the system call which failed. And P error has been invoked. There it's printed MK FIFO, but the operating system has added this text for us. File exists. So we've got a little bit of extra information from the kernel to tell us about the nature of the problem that was discovered when we asked our operating system to create a FIFO for us. So that's where the P error system call is very useful. We simply mention the system call that failed, and the operating system will add that extra information for us. Same deal if I manually remove the that now using the Unix rm command, remove, it's gone. And if I try and run the other program over here, which is expecting to find the pipe already in place for it, it's going to barf when it discovers, yes, there's no such file or directory. So I've tried to open the FIFO, which we know doesn't exist because I just removed it. and P error has been invoked. The operating system's caught the error and told us why it failed. Not you haven't got user permissions or some other cause of the system call failing, but the fact that it doesn't exist. All right. Anyone got any questions about that stuff? Okay. Well, when you've listened to these, and you might need a drink afterward, when you listen to these, those sample programs might make much more sense to you. And if you want to fiddle around with them again at any point, then they're in here. There they are there. And you can fiddle with those. We've got others to fiddle with too over the coming weeks. So the fork demo and the Hello World and the Control C and the alarm test and the pipe demos and FIFO demos, all the ones we've looked at are in that directory, in that folder there. Okay, getting on to the assignment. That we already know about. Down here we've got part B, the programming exercise, worth 30 marks, so we're getting a bit more serious now. What we've got here is a few different programming options, different topics. You don't do them all, you just choose one. But note that they've got different maximum marks because they're different levels of difficulty. Some people don't like programming, and me forcing them to do a difficult programming exercise, I've discovered over many years, doesn't really improve their learning. And so what I think works out better is for people who don't really enjoy programming that much, but nevertheless really need to do some of it before they can qualify for a pass in this subject, can do one of the options that isn't very difficult if they're prepared to forfeit a certain number of the marks. For those who enjoy programming, get stuck into it, they can choose a more difficult option, and if they don't tear their hair out in the process of completing it, then all well and good. So, differing levels of difficulty, you pick and choose, but differing amounts of reward as well. This first one is quite straightforward. It asks us to write some reasonably simple programs that time how long it takes for the operating system to create the process. So basically, before and after the fork system call, we get the system time, and we measure how long it takes. And of course, we should run that particular experiment many times over, and get the times that it takes, and see if we can produce maybe a histogram and make some informed comments on the amount of time that the operating system takes to create a process, and then compare that with the amount of time that it takes to create a thread. So we build another program here that creates a thread instead of a process, and we compare that with the amount of time that it takes to create a process. We should remember that threads are considered to be lightweight processes, that one of their virtues is that they're less expensive to create and schedule than processes, but by how much? Well, you can quantify your answer to that by completing that option for the assignment if you want to. So, two reasonably simple programs that use POSIX clocks. One simply uses the fork system call, the other one uses a pthread create system call. Run them lots of times over, maybe using an automated procedure for doing that, a similar sort of thing to what I did here with that batch file. So write a small batch file, get it to run your process creating program 100 times over and collect all the data, rather than doing it manually. Do the same sort of thing with your thread creating program. Same sort of thing. Collect all the data, whack it in the spreadsheet, and tell me what you found. So that's one option. Another one is to be using threads again. In fact, we can use threads or processes, whichever you prefer. It doesn't really matter. What this one does is it takes a file and it takes either two processes or two threads, and it positions the threads or processes at opposite ends of the file, and starts having them work towards the centre of the file by taking pairs of bytes in the file and swapping them around. And if the file is text, for example, after the two processes or threads meet in the middle, then our file is actually not readable. So we can take a text file, scramble it like this by swapping pairs of bytes, and the text isn't readable anymore. Of course, what we should be able to do is to run our byte swapping processes a second time, swap them back to their original places, and the text should be readable again. So we can scramble and unscramble the data. Not very secure scrambling, of course, but nevertheless effective enough at first level. The interesting part of this exercise is working out whether or not we can get a performance improvement over scrambling the file from beginning to end with one thread or one process. Does it take roughly half the amount of time if we've got two threads or two processes to scramble the same file, one starting from the beginning and one starting from the end? They work towards the centre and then they stop. All right, so that's what that one's all about. This one here is one that doesn't, strictly speaking, involve C programming. You can use just about any programming language you like to do this one, but create a simulator for a scheduler. We know how scheduling policies work. That was all covered in Chapter 5. And so what this is saying is create a program where we can have the user specify a number of tasks or processes and their arrival times and priorities where necessary, and the scheduling policy, and then hit go and have this program plot out the Gantt charts that we did by hand in the tutorials and the exam. There was one in the exam, of course. Write a program that does all that. The scheduling policies are round robin, shortest job first come first served, and non-preemptive priority, all the ones that we already know about. I could add some other ones in there, like rate and deadline monotonic that we're going to look at in the coming weeks, but I won't do that because we haven't looked at those yet, whereas you already know what all these ones are about, so you can make a start on that one straight away. That one attracts up to 30 marks if it's done well. Another one that we've got here is a toy operating system that used to run under Microsoft DOS and its clones. Back in the bad old days, before Linux became sophisticated enough for people to take seriously, whenever we had operating system subjects like this being taught all around the world, people used toy operating systems to get the students to have something to play with. And this is one such toy operating system created by a couple of characters at Purdue University. It was around for a long time. No one bothers with it anymore because we've got proper operating systems to play around with. We don't need these toys. However, it's useful enough to demonstrate quite a few of the concepts that we wouldn't otherwise get to see without just hand-waving. And what this particular assignment is asking you to do is to create a user-level library, right? So not a single application program, but a library that will emulate all of the operating system calls that this toy operating system has and convert them into real operating system calls on a Unix box. So, for example, the toy operating system, POSIX it can create a process by making a call to create. And there are sample programs that the toy operating system comes with that demonstrate how that actually works. And in the good old days when we only had DOS and 16-bit Windows on all the laboratory machines, then this used to work out quite well. It would use DOS simply as a loader, bootloader, and it would multitask programs even on 8086 based PCs, PCXPs. So it came with the ability to create processes, to create semaphores, and to do message passing. So it was a toy operating system, sure enough, but it could do the sorts of things that obviously we needed to be able to learn and demonstrate. However, it didn't use the same system calls as proper operating systems use. It used little sawn off ones, little cut down ones. What this is about is creating a library that we can link to a PC XENU user level program that will convert the PC XENU system calls into proper Unix ones. And the downloadable archive for PC XENU is there. So that's a DOS executable. We unpack it, you've got the entire source code to the PC XENU toy operating system, and you can start emulating the way in which it supported various system calls by converting them into Unix system calls. Last option is, if you don't like any of those, and you've got something else that you think you might like to do instead, then let me know and we can talk about it. And more than likely I'm going to say yes. So if you come up with some other assignment option, which is related, obviously, to the syllabus, that I haven't thought of, you think is more interesting, then email me and we can talk about it. That's not a problem. All right, getting access to a Linux or Unix environment. This will be necessary if you want to play around with any of the sample programs that I've shown you tonight, and the ones which we'll look at over the coming weeks. This is necessary, and there are a few different options. I've listed them all here in order of increasing complexity and as it says there, flexibility and versatility. First option that you've got for doing some Unix programming is using the dual boot machines in the IT computer lab. There are probably several other computer labs that have got this capability, but the only one I know for sure is down in the basement, room 400. You might know of others. So the PCs down there are set up to dual boot Windows and Linux, and you can just log in with your username and password down there, and get an up-to-date Red Hat Linux distribution booting up, and then help yourself. That's quite straightforward. You don't need to do anything other than just walk in there and log in. But what it does mean is that you can't do any kernel mode programming. You can't do a super user. And that limits your options a bit. And of course, you have to actually go into that lab to do your work there, which might suit you and it might not, because there are classes scheduled in there too. But that's a simple option if it happens to suit you. Next option is using the server rerun. That's the one that I was logging into tonight. You've got access to that as well. As I mentioned before, it's running Solaris, not Linux. That's where it's located, and accessing it is quite straightforward, as I showed you tonight. You just use the PuTTY secure shell terminal client. You can download that and install it on your Windows machine at home. It doesn't actually require installer, it's just a statically linked executable, only about 400 kilobytes. And you can download that, and then you can log into rerun externally, and that works quite well. The only disadvantage with that though is, well, the two disadvantages. We've only got a character mode terminal session, just like I was demonstrating tonight. We haven't got a full GUI desktop. And of course, again, we can't do super user operations. But that might suit you. The next option, and this is probably the best one for most people, is using a virtual machine. If we go to the companion website for the textbook, then that's this location here, os-book.com. Select our version of the text, that's the 9th edition, not the Essentials one, this one. And then down here, we can see Linux Virtual Machine in amongst the general resources. Select that. This provides us with a step-by-step procedure for installing a virtual machine on your own Windows box, which you can then use to run a distribution of Debian Linux. You download the open source VirtualBox by selecting here, so that link there, obtaining VirtualBox. Select Downloads, and select, because most of you will have Windows on your home PCs, I suppose, download that for Windows hosts. The problem is, we can't do that, I can't do it here, we can't do it on the lab computers because it requires administrator access. So it'll be perfectly fine for you to do on your own PC, but we can't do it here because it requires admin access. In fact, I can't even do it on my Office machine, which sucks. I tried it out on the Windows box that I hardly ever used at home, and it worked perfectly. It was quite straightforward, and probably the best approach for you to take. So you download VirtualBox from there, follow the instructions that the authoring team from the textbook will put here, and you've got yourself a virtual machine with a full graphical desktop and a recent distribution of Debian Linux. Works quite nicely. You'll also get root user access, of course, which is good and bad, because you might bugger something and have to reinstall the operating system. But that's not a critical failure in the sense that you don't have to repartition your disk or lose all your wares. You won't risk doing anything like that. So that's probably the best option, but as I say, I can't demonstrate it here. I'm sure those of you who read the instructions won't have any trouble doing it though, and that's probably the most satisfactory approach to take. Or if you're going to get into this stuff industrial strength, actually download a distribution and install it on your own PC. But be careful doing that if you're not comfortable doing things like repartitioning your disks. If you've got a separate PC that you don't use very much anymore, at home or wherever, and you don't need to maintain any of the data that's currently on it, you can just install Linux on that and you go for it. That's the industrial strength solution. And if you really want to provide yourself with lots of distractions and reasons to procrastinate, then that's the option for you. For most of us though, I think downloading and installing the VM would probably be the least hassle and give you the most flexibility and the greatest number of options. Alright, so does that all make sense? Who's got questions? Alright, I haven't actually put tutorial problems up for this stuff yet. So that's two things I've got to get done before next week. I'll put some tutorial problems up on this POSIX and Unix programming stuff, and the hardware time scheduling that we'll get up to, of course. So, oh yes, this practical lab session, location to be announced. I don't know whether we'll bother doing that now that we'll get access to the virtual machines, which I expect everyone will use. If we really want to do that, maybe we can, but I don't think it's really going to be necessary. Before the 15th of May, I'll put up the tutorial problems with the answers, and you can have a look at those. I couldn't put the answers up to the textbook tutorial problems, of course, because of copyright restrictions. But these tutorial problems here, myself and another guy who's retired put together a long time ago, and because we own them, we can put the solutions up. You can help yourself to those. So next week, we'll have a look at shared memory, semaphores, timing and memory locking, and so there'll be some PowerPoint slides with voiceovers at the end for that stuff, plus some much more interesting sample programs to have a look at. And then after that, we finally get on to the real-time stuff in the middle of May. Oh, yes, one last thing. With the recent alarm that was created by my master, we got a reminder, most of the staff, recently about using plagiarism detection software for submissions. And whereas I originally said there, I think just emailing your reports might be the easiest way to go, it's been put to me that perhaps we really should be doing this instead. So up the top there's a turn-it-in object, and you can submit your report from that. As for the programming part, I don't know, we'll work out what to do with that later, because there'll be source code and maybe reports and stuff. So that's a bit more complicated. Yes? Yeah, that's right. Yeah, due date's still down at the end of the semester. Yeah, whenever you want. Before the end of the semester. It's just instead of emailing it to me, we have to turn it in.
Animated GIF.
Yes.
That's how we can make websites.
Oh, as long as you think it's to deliver what it's asking you to do, yes. So it doesn't have to be massive, no. In fact, for this pretty straightforward one here, the one on startup times, your source code would be, you do the whole thing in probably 20 lines or less for processes, and then 20 lines or less for threads. So not very complicated programs, and then maybe a page or two of analysis. Yeah, so not much to that. All right. Okay. Well, read over those and think a bit more about them before making a choice. Or read over them and think a bit more about them before deciding you don't want to do any of them. And let me know, as I said before, whether you've got something else that you think you might like to do. Other than that,